In this lecture, we'll see the case when the memoryless nonlinearity lies in the K1 K2 sector where K1 and K2 are positive constants with K1 being less than K2. So we essentially are talking of nonlinearities that will possibly be in the following sector. This is the slope K1. This is the slope K2, and the nonlinearity of this form qualifies to be in the sector K1 and K2. So essentially, all nonlinearities lying between these two lines in this region. Okay, we'll be considering those nonlinearities in this discussion. Now we have already seen how to handle nonlinearities which lie in K1 infinity sector and 0 K2 sectors. So we'll use a similar approach to essentially get a condition on the LTI system that is in feedback interconnection with such a nonlinearity lying in the K1 K2 sector. So to do this, what we need to do is first transform the uh, nonlinearity psi to a equivalent nonlinearity psi tilde that lies in the 0 infinity sector, and that has two steps. Okay, so we need to transform the nonlinearity psi to psi tilde that belongs to the 0 infinity sector, and this will involve two steps. Okay, step 1, convert the nonlinearity in the K1 K2 sector to a nonlinearity in a 0k sector where k is a positive constant. The first step. Now, because we have got the nonlinearity in the 0k sector, we can convert this 0k nonlinearity to a nonlinearity that lies in the 0 infinity sector, and then any transfer function that is in feedback with a nonlinearity 0 infinity sector has to be strictly positive. That will give me a condition on how g of s should be. So we'll see the first step. So step 1. If you see here, we have k1 to be, and if this folds. Okay, so whenever xi is greater than equal to 0, k1 xi will be less than equal to phi will be less than equal to k2 xi, and whenever a xi is less than equal to 0, then we'll have k1 xi to be greater than equal to phi to be greater than equal to k2 xi. Now, in the xi greater than equal to 0 case, what we have is This similarly for xi less than equal to 0 case, what we have is this. So what this indicates is, if I have a system, if a nonlinearity, let's say psi bar, whose output is phi minus k1 xi, then this nonlinearity is going to lie in the 0k sector, where k is nothing but k2 minus k1. So this is a step where we have transformed the nonlinearity psi to a nonlinearity psi bar that lies in the 0k sector. So what is the transformation that we did? This is the psi nonlinearity with the input xi and the output phi. What we did here is we took xi, scaled it up by a factor k1 and subtracted it from phi to get phi minus k1 xi. So this is the new nonlinearity that we have got, which is psi bar. Okay, now we'll come to step 2. Step 2 is a familiar step, that is conversion of 0k sector to the 0 infinity sector. Okay, so this we have already seen. So what do? We want to convert the nonlinearity in the 0k sector to the nonlinearity in the 0 infinity sector. So for that, we already have psi bar, whose output is essentially phi bar. So what we do is, and the input here is xi. What we want is psi tilde, whose output is going to be phi tilde and the input is going to be phi bar minus, sorry, input is going to be k xi minus phi bar. Okay, this is k xi minus phi bar. To this, what I do is I multiply, sorry, I don't multiply anything. I just take phi bar as a feedback, add it to the input signal, and whatever input signal, whatever I get after this addition, I multiply it with k inverse and pass it as an input to the xi bar nonlinearity. Okay, so what we have here is the psi tilde nonlinearity that lies in the 0 infinity sector. So this completes the two steps that are needed to convert psi to psi bar. So if I see the entire picture, then what I essentially have is this is xi, this is psi, whose input is xi and the output is phi. What I do here is I scale up psi and I subtract it from phi. This gives me the first part of the non-linearity, which was basically the psi bar part, if you recall, right? And now the output of this has to be, if this is phi bar, the next part is I have a k inverse coming up with the input as k psi minus phi bar. Please note that this is what phi bar is, and the phi bar is taken as a positive feedback and is added up here. So if you see this, this is my psi tilde, which lies in the 0 infinity sector. Okay, here you should note that k is nothing but k2 minus k1. Okay, so this is the transformation that we see here in this particular case. Now if you look into the actual system G of S in feedback interconnection with psi, if this the origin of this has to be asymptotically stable, then we need a equivalent system. Let us call it as G tilde of S, which is in feedback with psi tilde nonlinearity, and this G tilde is strictly positive real. This is what we need. Now, how is this G tilde related to G? So, to find this out, we need to revisit the transformation that we had done for the nonlinear part. So, the transformation that we did for the nonlinear part is, so I'll redo it again. So, we have this, we have phi, the input is xi, we scaled up xi and subtracted it from phi to get the output phi bar. Now we had a scaling here, the input needs to be k xi minus phi bar, and this phi bar is taken as a positive feedback and added up here. Now again you should recall that This is u, this is y for the original system, and xi and phi for the original system. So we have u equal to minus phi and y equal to xi. So in the transform system also we have to ensure the same. So this is the g that we had, the input u and the output y. Now y is xi. So what I do is I multiply it by k, that gives me ky, which is k xi, to which I need to add minus phi bar. Where is this phi bar going to come from? So what I do here is just redraw it in a different color. This is plus. This is where phi bar comes in, and we'll label this, let's say, as u bar, the signal. So I tap this signal u bar and add it up here. So this gives me the required k2 is I minus phi bar. Now I want to get u. So what I do is I scale y. I scale it with k1. And subtract it from u bar. Right. So this is your g tilde. This is your psi tilde. So if you solve for this, what we need is that g tilde has to be strictly positive. So if we solve for this, what we get is g tilde is nothing but 1 plus k2g by 1 plus k1g. Okay, so what we conclude here is when psi is in the region k1 to k2, then 1 plus k2g by 1 plus k1g has to be strictly positive real, so that the origin of the autonomous closed loop nonlinear system, which is basically the feedback interconnected system, is asymptotically So what we have seen to conclude all the findings that we have got for this, when psi belongs to 0 infinity, G is strictly positive real. I write it as this: G tilde is equal to G is strictly positive real when psi is in K1 infinity sector. G tilde is G by 1 plus K1G, and this has to be strictly positive real when the nonlinearity is in the 0 K2 sector. Then G tilde is 1 plus A2G, and this has to be strictly positive real. And finally, case 4, when psi is in the K1 K2 sector, then G tilde is 1 plus K2G divided by 1 plus K1G, and this has to be strictly positive real, so that the feedback interconnected system's origin is asymptotically stable. Of the autonomous closed loop system to be asymptotically stable. When linearity are in this sector, then G tilde has to be strictly positive real, where G tilde is equal to either G or G by 1 plus K1G or 1 plus K2G, or a ratio depending on in which sector the nonlinearity lies. I suggest that, so we have seen when K1, K2 is positive, I suggest that you try to find out conditions when K1 and K2 are negative. Okay, when one of them is negative or both of them is negative, and so on, and see what happens in such cases. So we'll stop our discussion here. In the next lecture, we will see that if these conditions are to be satisfied, then with respect to the GS plane, where should the transfer function G's Nyquist plot lie when we are considering the single input, single output LTI system. So we'll stop here.